Here is today's problem. We need to solve 7 to the power of x plus 7 to the power of x equals 98. On the left side, two exponential terms are being added together. On the right side, there is nothing but the plain number 98. The number 98 is the target value that the left side must reach. An equation is a statement that two quantities have equal value. A balanced equation behaves like an old-fashioned weighing scale. Each side of the scale must carry exactly the same weight. The unknown in this problem is x, and it sits up in the exponents. To solve the equation, we need the value of x that balances both sides. Whatever we do to one side, we will also do to the other side. That way, the two sides stay perfectly equal at every step. Let us begin with the structure of the left-hand side. The first term on the left is 7 raised to the power of x. In that term, the number 7 is called the base. The letter x sitting on top is called the exponent. The second term is also 7 raised to the power of x. So both terms share the same base, the number 7. Both terms also share the very same exponent, the letter x. Since base and exponent both match, the two terms are identical. Whatever value x takes, the two terms will hold the same value. So the left side is one quantity plus a perfect copy of itself. One apple plus one identical apple always gives two apples. The size of the apple makes no difference to that count. The same counting idea works for complicated expressions too. Here, the repeated expression is 7 to the power of x. Adding the copy simply doubles the quantity, whatever it is. When one expression repeats, we can give it a temporary name. This renaming move is a standard tool for exponential equations. Equations with repeating powers often become simpler after renaming. Renaming also buys us a clearer view of the algebra underneath. So we introduce a new letter to stand for the repeated part. Let u be the value of the expression 7 to the power of x. Choosing a capital letter keeps the nickname easy to spot. The letter u is only a nickname, so the problem has not changed. Every appearance of 7 to the x can now be written as u. We rewrite the equation piece by piece using this nickname. The first term on the left is 7 to the x, so it becomes u. The second term is exactly the same expression, so it also becomes u. The right side is the number 98, and it stays just as it is. Our equation has now turned into u plus u equals 98. The unknown exponent is now tucked away inside the letter u. This is a linear equation in u, and those take only a few moves. U plus u means two copies of u added together. Two copies of u can be written more compactly as 2 times u. So the equation now reads 2 times u equals 98. The goal is to undo whatever is surrounding the unknown u. Here u is multiplied by 2, so the undo step is a division by 2. We divide both sides of the equation by 2. Dividing both sides by the same non-zero number keeps the balance. The number 2 is certainly not 0, so the division is allowed. On the left, 2 times u divided by 2 leaves exactly u behind. On the right, we need the value of 98 divided by 2. To divide comfortably, we can split 98 into 90 plus 8. Half of 90 is 45, and half of the remaining 8 is 4. Putting the halves together, 45 plus 4 makes 49. So 98 divided by 2 is 49, and the equation becomes u equals 49. That division checks out, because 49 plus 49 returns to 98. We now know that the quantity we called u is worth 49. By its definition, u stands for 7 raised to the exponent x. Raising the positive number 7 to any exponent gives a positive result. So u must be positive, no matter what the value of x is. Our candidate value is 49, and 49 is indeed positive. So u equals 49 is a perfectly acceptable value for u. With u settled, we can now bring back the original unknown. We replace the nickname u with the expression it stood for. That turns u equals 49 into 7 to the power of x equals 49. In other words, 7 raised to the mystery exponent must equal 49. The unknown x is sitting upstairs in the exponent position. To reach an exponent, the classic tool is the logarithm. We will use the natural logarithm, the logarithm whose base is e. The number e is a famous constant, about to 0.718. That constant appears all across growth and decay problems. The natural log of a number is the power of e that produces it. There is one requirement: the input of a log must be positive. Our two sides are 7 to the x and 49, so we check them both. The term 7 to the x is positive, as we discussed a moment ago. The number 49 is clearly positive as well, so both sides qualify, and we may take the natural log of each. Taking logs of two equal positive numbers gives equal results. the equation becomes natural log of 7 to the x equals natural log of 49. On the left side, we can apply the power rule for logarithms. The rule moves an exponent out in front of the log as a multiplier. In symbols, log of 7 to the x becomes x times the log of 7. The rule needs a positive base, and our base 7 is positive. There is a nice way to see why this rule is reasonable. Suppose for a moment that the exponent is a positive whole number. Then the power is just that many copies of 7 multiplied together. The log of a product of positive numbers is the sum of their logs. So the log becomes that many copies of log of 7 added together. Repeated addition of one value is multiplication by the count. That is exactly the multiplier the power rule promises. And the rule keeps working for any exponent, not only whole ones. Applying it here, the left side becomes x times natural log of 7. Our equation now reads x times natural log of 7 equals natural log of 49. This equation is linear in x, so one division will isolate it. We divide both sides by natural log of 7. A division is only safe when the divisor is not 0. Among positive numbers, only the number 1 has a log of 0. Our divisor comes from 7, and 7 is clearly not 1, so natural log of 7 is non-zero, and the division is justified. We arrive at x equals natural log of 49 over natural log of 7. Written out, that is a fraction with one log sitting on top of another. This quotient is already an exact answer for x. For any positive right-hand side, this same quotient shape appears. For our right-hand side, the quotient simplifies very nicely. Let us look more closely at the 49 inside the top logarithm. The number 49 factors neatly as 7 times 7. So the top is the natural log of the product 7 times 7. The product rule for logs applies here, since both factors are positive. So natural log of 49 equals natural log of 7 plus natural log of 7. A value plus an identical value gives to copies of that value. We used that exact counting idea on the left side earlier. So natural log of 49 is exactly 2 times natural log of 7. Since 7 times 7 is 7 squared, the power rule tells the same story. Now we substitute this back into our exact expression for x. We get x equals 2 times natural log of 7 over natural log of 7. The factor natural log of 7 sits on top and on the bottom. We checked a moment ago that this factor is not 0, so the matching factors cancel, and the fraction collapses. What remains is wonderfully short, x equals 2. We can also watch the same value appear through decimals. A calculator puts natural log of 49 near 3.8918. It puts natural log of 7 near 1.9459. Dividing those two values gives 2 on the calculator screen. The decimals agree with the algebra, which is always satisfying. The same division also works in log base 10. Log base 10 of 49 is near 1.6902. Log base 10 of 7 is near 0.8451. That division also lands on 2, since the base never changes the ratio. It also makes sense that only one exponent can succeed here. As x increases, the value of 7 to the x always climbs. For instance, 7 to the 1 is 7, while 7 to the 3 is already 343. For very negative x, the power shrinks towards 0 but stays positive. A value that only climbs can cross the level 49 exactly once. Every step we took was reversible, so no solution slipped away. So on the real line, x equals 2 is the one and only solution. The final step is to test the answer in the original equation. We substitute x equals 2 into 7 to the x plus 7 to the x. The first term becomes 7 to the power of 2. 7 to the power of 2 means 7 multiplied by 7. Working that out, 7 times 7 gives exactly 49. The second term is identical, so it is also 49. Adding the terms, 49 plus 49 comes out to 98. So the left side totals exactly 98 when x equals 2. The right side of the original equation is 98 as well. Both sides land on the same number, so the answer checks out. The whole check used nothing but simple whole number arithmetic. It is the same 49 plus 49 pairing that appeared when we have 98. So the solution of the equation 7 to the x plus 7 to the x equals 98 is x equals 2. To recap, we first saw that the left side was a doubled expression. We named that expression u, and the equation became 2 times u equals 98. Solving gave u equals 49, and returning to x gave 7 to the x equals 49. Logarithms brought the exponent down, and the logs then cancelled. That produced x equals 2, and the check confirmed it exactly. Thank you so much for watching this solution all the way to the end. If the video was enjoyable, a like is always hugely appreciated. And please consider subscribing to the channel for more math videos.